Hello everyone, I am Chenming Li from College of Mechanical and Electronic Engineering, Shandong University of Science and Technology. It is my great honor to share my research. The title of presentation is Dynamic Model and Robust Control. First, please let me introduce myself. From 2012 to 2016, I was an undergraduate student in Hefei University of Technology. Then, from 2016 to 2022, I pursued for Ph.D. During this period, I studied in Georgia Institute of Technology as a joint Ph.D. student. And now, I am an academic professor in Shandong University of Science and Technology. My research interests including dynamic model, robust control, game theory, and fuzzy theory. There are some relevant papers that have been published in international journals or conferences. I was also fortunate to be awarded such as Excellent Doctoral Graduates, National Scholarship for Doctoral Students. As for my research field, it revolves around uncertainty. It cannot be avoided in complex mechanical systems and complicated environments. For example, the unknown system's parameters and unpredictable disturbances. So it brings a great challenge to establish an accurate model and design an effective control. In my research, we proposed a four-step procedure to solve this problem. First, we apply the inequality constraints to build the bounds of system inputs and outputs. Then, the fuzzy set theory is merged into system theory to obtain the fuzzy dynamic model. Third, a novel high-order control is designed to compensate for uncertainty. Finally, a game theory-based optimization approach is formulated to solve the optimal parameters. Now, let's discuss them in details. Equality constraints. They can be used to limit both input and outputs. To satisfy them, the diffeomorphism and state transformation approaches are proposed for input and output respectively. First, for input. Suppose there is a system x dot equals to f plus b capital phi plus be, where x is a system state, b is a matrix of input, phi is input, and e is disturbances. Then we transform the original input omega into a new input u by using a bounded function. Of course, to ensure the stability of the system, there are certain restrictions when designing the channel head phi that controls u into the system. For the output, we use a transformation function alpha to change the original state psi into zeta. For example, supposing alpha is a log function and designing as zeta equals to log psi minus psi m over psi d minus psi m. In this equation, psi d is the desired trajectory and psi m is a minimum value of psi. In this way, we have psi approaches to psi d when zeta approaches to 0, and psi has a lower limit, however zeta belongs to negative infinity to positive infinity. The left and right figures show that the control inputs and system outputs with inequality constraints. It can be concluded that the fluctuations which are caused by uncertainty can be suppressed. Next, the nature of uncertainty is further investigated based on fuzzy set theory. It is first introduced in 1965 by Zadie. In this field, the most common way to describe uncertainty is based on probability theory, which is a representation of the frequency of occurrence of an event. This kind of interpretation requires a large quantity of data. However, the data source of uncertainty cannot be obtained or repeated easily in many practical systems, such as earthquake data. As an alternative way, We describe uncertainty in a fuzzy view, which is a representation of the extent of occurrence of an event. To be more clear, this fuzzy model is totally different from the very popular TS model or other fuzzy if-then rules based on models. It is based on fuzzy set and apply membership function to measure uncertainty. Then we need to compensate for it. The solution is to design a high-order robust control. The specific form is different according to the system is linear or nonlinear, while the high-order term is similar, that is mu. The control U includes three portions. The first portion, R minus 1 B transport Px, is to maintain and drive the nominal system to be on the desired trajectory. The second portion, gamma mu R minus 1 B transport Px, is to suppress the effect of the uncertainty on the system performance. The third portion V is to release the burden of the control by compensating for known disturbances. Among these, the most important part is the high-order term mu. It consists of three portions as well. The red portion is used to compensate for uncertainty. The parameters delta 1 and delta 2 are relevant to the fuzzy uncertainty bound. The green portion is used to analyze stability. The yellow portion is used to adjust the amplitude of the high-order term. Based on this, the uncertainty system can be proved to be uniformly bounded and uniformly ultimately bounded. To find a better system performance and lower control cost, the game theory is applied to solve the optimal control parameters. According to the relationships among them, we apply the cooperative game, non-cooperative game, or stack-burger game, respectively. The cooperative game can be explained with the following figure, and the best decision is called proto-optimal. The basic principle is that any player unilaterally leaves the proto-op point, resulting the cost increased for at least one player. For the non-cooperative game, the best decision is called Nash equilibrium. The basic principle is that any player unilaterally leaves the Nash equilibrium, leading to a higher cost at least one himself. The stack-burger game divides the players into leaders and followers. This game logic can be used in cases where the degree of influence of the control parameters on the system varies considerably. For an optimization problem, we need to select the players in a game, which are the tunable parameters. Their values decide the uniform bounds. Then, the decision set should be clarified. At least, the control cost functions of each player are designed. An experiment is performed by a collaborative robot. The whole design procedure is shown in this figure. It can be divided into model, control, and optimization part. The experiment and simulation results show that for a fuzzy dynamic system with inequality constraints, by applying the optimal parameters in high-order robust control, the errors are reduced without increasing the cost of input. Thank you.